Thank you. Yes, so thanks to the organisers for inviting me to this lovely conference in a lovely city. So Griffith University, for those who don't know, is here on the east coast of Australia. That's where I am, and that's where Michael Hall is. The other co-author on this work, and I should say that I guess these co-authors just refer to the last part of my talk. But the other one is Dirk-Andre Deckert, who's currently at University of California, Davis. Okay, so as you can see, I'm ambitiously trying to cover a lot in my talk, and a lot of things that have come up elsewhere and will continue to come up elsewhere in the conference. And so I'm going to basically try to cover the first two topics fairly briefly, that is weak values and their relation to Bohmian-like trajectories. And then for the second half of my talk, hopefully talk mainly about this topic of many interacting worlds. Okay, so weak values have been introduced by, or been mentioned, I should say, by a couple of people, but I'm not sure there's been much of an introduction, so this is just a couple of slides explaining what weak values are. So they're introduced in this paper from 1998 by Aharonov, Albert, and Wiseman. So this is my explanation of what they did. So essentially they're considering a system coupled to a probe. So the probe is just going to be treated as a particle with a position and momentum, prepared initially in a minimum uncertainty state. So that means that the probe state is defined by just three numbers: the mean initial momentum, the mean initial position of the probe, and the uncertainty in the momentum of the probe, because being a minimum uncertainty state, the uncertainty in the position is just like the reciprocal of that, essentially. And so, yeah, so the system is going to be coupled to some operator in particular of the system, some arbitrary operator A, by a von Neumann style of coupling like this. So that couple is basically causes a force on the probe here, so that after the interaction, the momentum of the probe has shifted. So these are Heisenberg equations relating just before and after, and saying basically the momentum of the probe shifts by an amount exactly equal to the operator A for the system. So what that means is that we can use this probe to estimate that operator A for the system, and in particular I can simply measure the final momentum of the probe here and take off ideally if I could take off the initial operator for the momentum of the probe, then I would get exactly A, but of course I can't, in the lab, subtract an operator from a measurement result. All I can do is subtract the mean of that operator, which I know, the mean of the initial momentum, and use that as my estimate for this observable A for the system. Okay, so if I do this experiment over and over again, every time preparing the system in the same initial state, psi in, then what you'll find is the expected value of that estimate is exactly what quantum mechanics gives for an average value for an operator. Okay, that Born rule expression there. Okay, so there's nothing particularly interesting in that, but it becomes more interesting when we also consider not just making this momentum in here, but we have the system has gone through this interaction. We can still do something to the system. So for example, making a final measurement here projecting onto this state phi f. Okay? And so then we can also say, well, when I say projecting, what I mean is we make a measurement and it may or may not project the system onto state phi f, but let's consider the subensemble where it does, okay, where I get the result phi, that yes, it was in state phi f at that point. And so then I can consider, so I still have this information down here by which I'm estimating A, but now I can consider that expectation value on the subensemble where not only did I prepare in the state psi in, but I projected on the state phi f finally. And so what Aharonov, Albert, and Wiseman showed was that in the limit of a weak measurement, which is sigma p going to infinity, that expectation value, the pre- and post-selected expectation value, is equal to this expression here, the real part of this ratio. So the point about that is that this ratio can be arbitrarily large, okay? Because on the bottom, is this inner product between the initial and final states, and if that's small, then this can be very large, and that's why, and I should have pointed it out 2 slides ago, that's why they could write a paper with this title like this, of how the result of a measurement of a component of the spin half particle can turn out to be 100. Okay, so what they meant by that was that the weak value, this expectation value is defined here, could be 100. It could be anything you like. Okay, but why is this the weak? I just called it the weak measurement limit, and I called this thing a weak value, which is what they called it. But why is this the weak measurement limit? Well, it's because there are 2 ways of understanding, and they're both sort of necessary to understand. So first, it's weak in the sense that you get very little information in any measurement that you make, and that's we can see by looking at the operator for this estimate of A. And so that the operator is the actual observable A plus this term, which is the difference between the initial momentum of the probe and its mean value. So in the limit where the uncertainty in the initial momentum of the probe goes to infinity, clearly this operator here, this contamination, this noise term here, has a very large mean square value, which goes to infinity in the absolutely weak limit. But it's also weak, and this is crucial, not only, so this is necessary to have this, to call it a weak measurement, but it's also necessary for it to be weak in the sense of causing very little disturbance to the system, okay? And that's a consequence of the assumptions we've made, because I can look at an arbitrary system operator, I can look at its final value for that system operator. It turns out to be given by this expression here, and so it involves this initial position of the probe, and precisely in the limit where sigma p goes to infinity is where the mean square value of q in goes to 0, because it's simply the reciprocal of that, because it's a minimum uncertainty state. Okay, so that's why it's called a weak measurement, and that's why we call this thing a weak value. And so the point is that, yeah, it's still a value obtained in the same way as we obtain expectation values in any experiment. We have to repeat the experiment many times, and in fact, because we're dealing with a weak measurement, we have to repeat the experiment even more times than you normally would, because every individual result has a lot of noise in it. So essentially, you have to do even more work, but the basic idea is the same for getting the ensemble average. Okay, so weak values have been mentioned a number of times in this conference. So this is just some general remarks I've said about, why are they coming up? What's my opinion about why weak values turn up in these sort of discussions of fundamental questions in quantum mechanics. And so I think for me, the answer is that there are a lot of questions that we can ask. Classically, we'd have no trouble understanding, but in quantum mechanics, there just is no answer, or at least it's an ambiguous answer, and so what do we do? And so what I think is the advantage of weak values is that they do offer answers. In some cases, it may be a completely new answer to the question. In other cases, it might single out one of the answers which has already been proposed. But in either case, I think that this gives new insights into the phenomenon and can prompt new research. Even if it doesn't, at least what it can do is enable an experiment to be done, and that's a good thing in itself, not least because it typically brings the issue and the foundational issues to the attention of a much broader audience than theoretical papers typically do. And so there are many examples of this. I'm not going to go through them. Some of them you've heard about already. Some of them I'm sure you'll be hearing about later today. And yeah, I'll just go on that. But what I'm going to talk about is the application to measuring Bohmian-like trajectories. Okay, so Bohmian mechanics has also been introduced today. Or maybe even yesterday. So this is the way I'm going to describe it, is that what we have is I'm going to call it a world configuration, so I'm considering a system could be many particles, and so Bohmian mechanics says that you have a definite configuration which evolves according to some velocity, which is determined by the wave function. Okay, that's broadly what Bohmian mechanics is about. Now the point is that there are actually infinitely many functions of the velocities which I could choose, which will satisfy this continuity equation. So why choose the particular one that is the standard one in Bohmian mechanics? Well, what I suggested a few years ago now in this paper in New Journal of Physics was that we can motivate a particular expression for the velocity in terms of weak values by considering, well, what would it mean to measure the velocity of a particle if you were a completely naive experimentalist that didn't know anything about quantum mechanics? Well, you might discover that in general making measurements seems to do something nasty to your system, but nevertheless you could also make the measurements weaker and then it seemed to be less nasty. And so then you could say, okay, so the definition of velocity is the difference between two positions divided by the time elapsed. And I want the velocity at a particular point, so I'm going to take that time elapsed to 0. But I want to make the first measurement not disturbing, okay? So I'm going to make a weak measurement at time t, then a strong measure. Oh, we're having a disturbing measurement going on there. A weak measurement at time t, a strong measurement a short time later. Look at the difference between those two results, conditioned on the strong measurement showing that the particle is at point x, which is the point at which we want to know the velocity. And so in terms of weak values, I can write it like that. And when I work that through, it turns out that this gives you the standard Bohmian expression for the velocity. But more interestingly, as I pointed out in this paper, this is, as I was saying, something you can actually go and do an experiment for. And so we'll be probably seeing this again. But so this was the experiment done in the lab of Ephraim Steinberg, the Kostis et al. Paper published in Science a couple of years ago. So you probably hear they actually did things slightly differently from what I just described. But nevertheless, the basic idea is similar. So I do want to stress, and I guess the other people as well, that this is not actually following the motion of individual particles. This is patching together little bits of velocities measured locally at individual points. Okay, so these are reconstructed velocities because the theory doesn't say that you can actually follow the particles. It just says you can measure the velocity at any given point. Okay, so I haven't shown you the expression for that velocity, and those who are familiar with Bohmian mechanics will know what it is. But what we could ask a broader question is, in general, what does that formula give that I wrote up here? What does this give for the velocity? And the answer is this expression here. So here I've made no assumptions about the Hamiltonian, about dynamics at all. So everything is just written in terms of the Hamiltonian and the position operator or position states. So the question you could ask is this always actually consistent with quantum mechanics? Does this form of the velocity, in fact, propagate an initial probability distribution for the configuration to a final probability distribution which still agrees with quantum mechanics if the initial one does? And the answer is it does if and only if the Hamiltonian here is at most quadratic in the operators which are canonically conjugate to the position operator or the configuration operator more general. And so you could say, well, isn't this a limitation of the approach because it only has limited validity? And I'd say no, because it turns out that, well, of course, as we know, that all physical Hamiltonians are so constrained. Basically, all the Hamiltonians we know of are quadratic or, well, at most quadratic in the momentum variables, and that's why the formalism all works. Of course, that works as long as we take the hidden variable, as long as we take x to be the configuration, to be the position of all the particles in the world. So rather than being a limitation on the theory, I actually see this as a boon in the sense that it tells you that you have to choose the hidden variable to be the configuration. You can't choose it to be the momentum, for example, and say that the reality of the world lies in the momentum of particles. If this theory is going to work, the reality has to lie in the positions of the particles because of the nature of the Hamiltonian, and that's an objective fact of the world as far as we know what the Hamiltonians are like. Okay, so does this actually prove then that Bohmian mechanics is correct and the positions of the particles must be the reality? So I want to be clear, I'm absolutely not claiming that, okay, because this whole thing is predicated on the idea that I have to choose some hidden variable, and of course not everybody believes with that. But what and certainly even if you do, you don't have to believe that its velocity is governed by a weak value. which can be experimentally measured. But what I think it shows is that it doesn't show the theory is correct, but I think it shows that it's self-substantiating in the sense that Bohmian mechanics, well, if you choose this, then you get a theory in which if you go out and do an experiment according to that theory, you would measure a weak value which would be in accord with the velocity in the theory, and so that makes it, I think, a very attractive and natural theory, but it doesn't prove that it's necessarily correct. Okay, so going on then to the last topic in my talk. So here's a picture again of those trajectories. Here's another one, which is, that's a purely theoretical one. So everyone's seen pictures like this before. If you didn't know anything about quantum physics or whatever, what you might look at these pictures and think is that this is describing a bunch of particles which repel one another, because you can see the trajectories don't cross. So if you were completely, if you didn't know anything about streamlines or anything, if you just might say, oh, I've got a whole bunch of particles here and something, they've got an interaction repelling them so that they don't cross. So of course, what we normally say is we don't take this literally. There's no actual bunch of particles, there's only one particle. I'm just plotting the different possible paths it could be taking. But why? Why not take this literally? And so this, in fact, so we heard from Bill Poirier this morning. I'm very glad to have met Bill now, on this idea of taking literally the idea that you have an ensemble of particles all obeying Bohmian mechanics or something like Bohmian mechanics, rather than just an individual one. And so, as you said, the work was published last year. So actually, around the same time this was published, and not knowing about his work, I, and Michael Hall and Dirk-Andre Deckert, had a very similar idea, but it's different in, I think, one crucial way at least, in that for us at least it's difficult to imagine what a continuous ensemble actually means. And so what we're trying to do is to develop a theory for a finite but extremely large ensemble of particles, well, I shouldn't say, ensemble of worlds, I should say, describing, for example, in this case, even a single particle. So let me jump to the one-dimensional case just to show what I'm thinking about. So I'm describing a single particle here, just as those pictures are meant to be describing. But it's a many worlds theory of that single particle. Okay? So a single world in this nomenclature is a single non-relativistic particle with certain mass. It could be in some potential. But what I'm going to consider is many worlds, okay? So I have, therefore, many positions that I have to consider. It's in one dimension, so I can order those positions. So xn plus 1 is greater than xn. And I'm going to assume here that those worlds are going to be arranged with a slowly varying interworld separation. So they're fairly evenly, they don't have to be evenly spaced, but when they become the spacing itself only changes slowly. So in other words, the difference between spacings between neighboring worlds changes, the difference is of order n to the minus 1, where n is the number of worlds. I'm also going to assume that the initial velocities of those worlds are smoothly varying in the same sense, okay? That if you have two worlds which start off close together, their velocities are going to be close as well. Okay, so I could think of these initial spacings and initial velocities as defining a wave function according to the usual Bohmian. If I take those velocities and 1 over the separations as being some representation of density, then I can write down a wave function which corresponds to these initial conditions, okay? But the crucial point here is that I'm talking about a theory in which there is no wave function, okay? There is only the ensemble of worlds with their initial positions and their initial velocities, okay? So that's the crucial thing. There is no wave function in the ontology of our theory. Our ensemble of worlds is a real ensemble, not a virtual ensemble, and it's necessary that they all be real because we're going to postulate that those worlds interact, okay? So this is quite different from the Bohmian approach. We're actually postulating then that we have this equation of motion, This is the Newtonian force, and then this is a non-Newtonian force, extremely non-Newtonian in the sense that it's actually interacting worlds, interacting parallel universes, if you like. And so what it's saying is that this is I call it a three-body interaction, but of course that's, it's an interaction between three nearby parallel universes, in this case. And so when I call the local potential, it's local only in the sense that nearby parallel universes interact, but they don't interact with far away parallel universes, but it's obviously not local in any ordinary sense of that word. So the specific three-body potential which we consider looks like this one here. So it involves h bar, as you can see, so it's a quantum effect. And I won't go into details. You can stare at that for a couple of seconds if you want and see if you can make anything of it. But it's not that obvious what you can do. But in any case, it's clearly, well, I suppose one thing you can take from it is you can see that it blows up if the particles get too close together. Okay, so if nearby universes, parallel universes, nearby worlds, if the particle position gets too close together, then this potential blows up, and so of course this is going to prevent that from happening. And what we believe is that with those initial conditions I talked about, if we take the limit n goes to infinity, that we believe that this potential will actually result in an ensemble which is equivalent to the virtual Bohmian ensemble for that wave function. And so here's some actual solutions of that equation. So I hope you can see that looks reasonably good from here. So this is just solving those dynamical equations for 100 worlds, so not very many at all. And what you can see, so I should point out, so the overall shading is just actually the mod squared of the wave function, where the wave function was defined, as I said before. The red curves, the nice smooth red curves, is the Bohmian ensemble, but this is just picking, I don't know, 10, 12, how many worlds there are here. It's just some sub-ensemble of the actual 100 which we generated, which is these blue curves here. So what you see is that up to some break time at least, which is around about here, solving those that many interacting world equations does give you good agreement with the Bohmian equations guided by the wave function. In our theory, there is no wave function. It's just the worlds interacting with neighboring worlds. After that break time, things go haywire. But I'm told Dirk actually is the one who did these simulations, that as you increase n, that break time becomes longer. So it doesn't seem to be any sort of fundamental thing as far as we can tell at the moment. So basically, it seems like it's promising. The idea seems to work. At least it seems to be able to reproduce, to some extent, the interference pattern from a double slit experiment. Okay, so I think I'm probably getting near to, yeah. So I'll rush, okay, I should point out, so there's a bunch of things which we can show analytically from our many interacting world dynamics. We can show Renfest theorems, we can show various things which are common in classical and quantum mechanics. We can explain effects like non-classical barrier penetration, and we can solve some simple systems like harmonic oscillators, and it all seems to work with them. I'll just say very briefly that we've thought about how you generalize this beyond the simple one particle in one dimension, and it becomes a lot more complicated. We don't have any explicit form of the potential that we know would work, but the basic idea is captured by this equation here, that every world, again, obeys a Newtonian. This is just Newton's equation. So the only thing which we're doing is adding some quantum force, which is exactly the force from Bohm's quantum potential, but we're imagining that quantum force is determined by some sort of local averaging of the density of worlds in the region for where that particular world is. Okay, so it's probably important to say something about how we understand this theory. So I want to, as I stressed before, like we are considering a real ensemble of worlds. So all worlds are equally real. Your consciousness supervenes on only one of those worlds. And if you think that's odd, well, you should just remember that, of course, in this world, your consciousness only supervenes on one part of it as well, which is you. So I don't think that that's particularly surprising. So there's no wave function, so of course there's no wave function collapse. So the effective wave function collapse is just a consciousness on one world updating its idea about which world it is likely to be supervene upon, if we put it that way. And so yeah, we, in the same way that Bohmian mechanics or the regular many worlds interpretation is believed to agree with standard quantum mechanics, we think that our theory would be the same. Yeah, I'll leave that thing. Okay, so let's move on to the conclusions. So I've talked about weak values and how they can shed light on fundamental questions, in particular, picking out a unique Bohmian velocity. And when you look at these pictures, this suggests, at least to me, this idea of an ensemble of worlds with mutual repulsive interaction between nearby ones. And what we've done is shown that that intuition can be made precise, at least in the one-dimensional case, with an explicit three-body interaction. And clearly there's a lot of work remains to be done to see if this is a viable theory. Thank you.
Thank you for your clear presentation and sticking to the time so well. So we still have time now for a few questions. Yes, please.
Only to both last speakers, may I ask you, your slits, or when you draw these trajectories, they are Gaussian slits, or have you rectangular slits? Or is there a difference, or what would be the difference on that?
Yeah, this simulation I think is Gaussian slits. I think back here, these are probably rectangular slits in, actually I'm not 100%, yeah, this case is probably also Gaussian in the experiment. Do you want to comment, Boris?
I mean, these are essentially Gaussians, but they're truncated by some physical object, so.
Okay, so it sounds like the answer to your question is basically Gaussian in most cases.
Would there be a strong difference, or you would not say too much? Okay.
Okay.
Yes, so I will ask my question. I'm not so much pleased by your use of the word worlds. In general, I have to deal with one world, but let me ask you...
Well, you are in one world, but you have to deal with many.
Yeah, but I want to stay here. Now, let me ask my question the following way. Suppose you will describe the air molecules in this room, this ensemble of particles. Would you also then use the words many worlds?
Absolutely not. No, because an air molecule is not a world. So the point is that a world is something extremely rich. So this is what I talked about here is a toy model, of course, of a world, of the one-dimensional particle. I mean, the real theory, of course, is that a world corresponds to this configuration, which is the configuration of all the particles in the world. So all the air molecules in all, you know.
We take this room, that's enough for me.
Yeah, okay, sure. So all the air molecules and all the molecules in the world. So a nearby world will be one in which all of those particles are in almost the same positions.
This is called state or so in phase space, in classical phase space.
Well, it's in configuration space rather than phase space here, but yeah, sure. I mean, I called it a configuration, but I call it world because this is the term that's used in the many worlds interpretation, and I think that it's basically a similar idea to that.
Exactly for that reason I'm unhappy about it, but okay.
Yeah, regarding the issue of the slits, yes, there are important differences. I mean, it's not the same to compute with squares, I mean, just total transmission, than with a Gaussian, because the function, I mean, the fraction on function itself is going to cause you a modulation of the interference. So, for example, in the case of a full transmission, what you obtain is a very fast flow of, quantum flow towards slits. So it makes that, that in between the two slits, the emergence of the pattern, I mean, this non-crossing appears before. With the Gaussian, you get a very fast attenuation, so you don't see this sort of second maximum and so on. In the case of the experiment, for example, we tried with Gaussians, and it goes pretty well. But then, if you truncate the Gaussians, you get some oscillations in the sides that are that they very nicely fit those initial oscillations that can be seen in the experiment. Now, for example, we are working out a model that dates back to the 80s by Starshan and other people from laser physics that can describe very well the experiment. And this is with Gaussian beams.